Think about this for a moment. 54 years ago, a human being left footprints on the surface of the moon. He stepped onto a world that is not Earth, looked back at our planet, and saw something no one had ever seen with their own eyes before. A small blue disk suspended in nothing, silent, fragile, beautiful. And then he came home, and no one has gone back since. Not a year later, not 10 years later, not 50. Half a century has passed, and the moon has remained exactly as it was, empty, silent, with those same footprints still perfectly preserved in the soil, because up there is no wind to erase them, no rain, nothing to disturb them. They are still there, right now, while you are listening to this. Neil Armstrong's footprints, Buzz Aldrin's footprints, frozen in time like fossils from an era that feels further and further away with every passing year. And the question, the real one, the one many people ask quietly, is not simply, why haven't we gone back? The deeper question is, why, with all the technology we've developed in the meantime, with the computers we carry in our pockets that are more powerful than the mainframes that carried those astronauts to the moon, with the most advanced rockets in human history already being tested and launched, why is that surface still empty? The official answer you probably already know. Reduced budgets, the end of the Cold War, shifting political priorities, and those are all partly true answers, but they also always feel a little insufficient when you really think about them. Because behind every stated reason something more complicated hides, something more human, more difficult to admit. Before we go any further, let me ask you something. Where are you listening to this right now? What time is it where you are? Are you already in bed with the lights off and the sound coming from a screen resting on your nightstand? Are you sitting somewhere in your home in a quiet spot while the world outside keeps making its noise? Whatever the case, you are in the right place. Because what we are about to explore is one of those subjects that seems simple on the surface, but the more you look at it, the more you realize it hides layer after layer of history, politics, science, fear, and something that very closely resembles human ambition at its most contradictory. Tonight we will move through all of it slowly, without rushing, each piece in its place. Let's begin at the beginning. Not with Armstrong setting foot on the moon, much earlier than that. At the moment when someone, in a meeting room in Washington, decided that going to the moon was necessary, not for science, not for exploration, for something far more earthly. It was 1957, and the world had just received a signal, not a metaphorical signal, a real, physical one, transmitted into space. A small metallic object launched into Earth's orbit had begun emitting a steady beep, detectable by any radio amateur on the planet. It was called Sputnik 1. It was Soviet. And that beep, simple, monotonous, relentless, had triggered something historians would later call the Sputnik crisis. Because that beep was not just saying we are in space. It was saying something far more precise and far more threatening. If we can put this in orbit, we can put anything in orbit, including a nuclear warhead, including something aimed at you. The United States was horrified, not technically, or at least not only technically, they were horrified psychologically. The idea that the Soviet Union had the ability to dominate space meant something very specific in that historical moment. It meant that the battlefield of geopolitical confrontation had just expanded upward, beyond the atmosphere, into a territory no one had yet claimed. And so the race began. Not toward the moon, at first. Toward orbit, toward satellites, toward the first astronauts. But the moon quickly became the symbol of everything, the most visible, most dramatic, most definitive point that could be imagined. Whoever reaches the moon first wins. Not a battle, a narrative, an entire era. Kennedy understood this before most. In 1961, standing before the United States Congress, he spoke those words many people still remember. Before the end of the decade, the United States would land a man on the moon and return him safely to Earth. Not because it was easy, he said, precisely because it was hard, and on that difficulty, on that enormous, expensive, dangerous challenge, one of the most extraordinary endeavours in human history was built, not out of love for space, out of love for winning. What is rarely told, at least not in the simplified version of the story, is how fragile that victory really was, how much it was built on enormous pressure, impossible deadlines, and risks that engineers understood perfectly well, and that politicians preferred not to communicate to the public. The Apollo program was a miracle of engineering, but it was also an undertaking that had already nearly killed its own people before anyone ever reached the moon. In January of 1967, during a routine ground test, a fire broke out inside the command module capsule of Apollo 1. Within seconds, the interior filled with flames fed by a pure oxygen atmosphere at high pressure. Gus Grissom, Ed White, and Roger Chaffee, three of the most experienced and respected astronauts in the program, died before a single rocket had left Earth bound for the moon. The program was frozen. Investigations were launched. Engineers went back through thousands of components, thousands of connections, thousands of decisions that had been made under the crushing weight of Kennedy's deadline. And what they found was troubling. Not because anyone had been careless, but because the schedule had been so aggressive, the pressure so relentless, that certain risks had been accepted in ways that would never have been acceptable under normal circumstances. This is an important thread to hold on to, because it runs through the entire story we're going to explore tonight. The moon was reached not in spite of the pressure, but in many ways because of it. The pressure compressed years of development into months. It pushed engineers and astronauts and technicians to limits they might never have approached otherwise. And it produced results that were genuinely astonishing. But pressure is also a strange force. It can build extraordinary things, and it can also be the reason those things stop once the immediate motivation disappears. After the Apollo 1 fire, after the redesigns and the investigations, the program continued. Apollo 7 flew in 1968. Apollo 8 carried humans around the moon for the first time that same year, a mission that produced one of the most famous photographs ever taken, Earthrise, the image of our planet rising above the lunar horizon as seen from lunar orbit. Apollo 9 tested the lunar module in Earth orbit. Apollo 10 flew to within 9 miles of the lunar surface in a full dress rehearsal, without landing. And then came Apollo 11, July 1969, the entire world watching, televisions in living rooms, in bars, in public squares, an estimated 600 million people, 1/5 of the entire human population at the time, following the transmission in real time. Armstrong's voice crackling through static, the descent, the dust, the words. One small step. It was real. It happened. It was not a simulation or a rehearsal. A human being stood on the surface of another world. And the Soviet Union, which had pushed the United States to this point with a decade of competition, which had been the first to put a satellite in orbit, the first to put a human in space, the first to conduct a spacewalk, the Soviet Union said almost nothing, because they had not made it there first. And in the logic of that era, second place was the same as losing. The race was over, and that, quietly, almost invisibly, is where the real story of why we have not gone back begins. Not with budget cuts, not with political decisions, with the moment the reason for going disappeared. Because here is the thing about the Apollo program that is easy to miss when we look back at it with admiration. It was not primarily a scientific mission. It was a geopolitical statement, a demonstration, a proof of capability directed not at the moon, but at Moscow, and at every nation watching the two superpowers compete for the future of the world. Once that statement had been made, once the flag was planted, the photographs taken, the moon rocks collected, and the astronauts returned safely, the question that no one had dared ask during the race suddenly became unavoidable. What exactly are we going back for? That question, what exactly are we going back for, didn't kill the Apollo program immediately. It took a few more years, a few more missions, and a slow accumulation of political and economic realities to do that. But the question was there, hanging in the air from the moment Apollo 11 splashed down in the Pacific Ocean on July 24th, 1969. In the months that followed, something subtle began to shift. The American public, which had watched the first moon landing with a kind of collective breathlessness, was already beginning to move on. Apollo 12 launched in November of 1969, just 4 months after Armstrong and Aldrin had walked on the lunar surface. It was a successful mission. The astronauts landed in a different region of the moon, collected samples, conducted experiments, and returned safely. It was, by any reasonable measure, a remarkable achievement. But the television networks did not carry the full broadcast. Ratings had dropped. People had seen men walk on the moon. Seeing it again, without the historical weight of the first time, felt to many viewers like a repeat, not a new chapter, a rerun. This might sound like a small thing, a matter of public attention and television scheduling, but it points to something much deeper about the way human beings relate to exploration, to risk, and to the extraordinary. There is a psychological phenomenon that researchers and historians have observed across many different fields. The way that once something previously impossible becomes possible, it very quickly begins to feel ordinary. The first time a human runs a 4-minute mile, it seems like an absolute limit of human physiology, an almost supernatural barrier. Within a few years of it being broken, dozens of runners cross that threshold regularly. The barrier was never physical, it was psychological, it was the weight of the word impossible. The first moon landing carried the full force of that psychological barrier. Nothing like it had ever happened. The tension of not knowing whether it could be done, the fear that something might go catastrophically wrong, the sheer novelty of watching a human being step onto another world for the very first time in history. All of that combined to create a moment of collective attention that may never be replicated in quite the same way. The second landing could not carry that same weight. The third could not either. And so the audience drifted as audiences do toward the next new thing. Meanwhile, inside NASA and inside the halls of Congress, a different conversation was taking place. The Apollo program was extraordinarily expensive. At its peak, NASA's budget represented approximately 4% of the entire United States federal budget. To understand what that means in practical terms, consider this. Today, NASA receives less than 0.5% of the federal budget. The Apollo era was a moment of spending that had no precedent in peacetime science and engineering, and that very few people in Washington were eager to sustain once the primary goal had been achieved. President Nixon, who inherited the moon program from Kennedy and Johnson, was not particularly invested in space exploration as a long-term national priority. He congratulated the Apollo 11 crew in a phone call from the Oval Office that has become famous, but his administration's relationship with NASA was complicated from the beginning. Nixon's attention was directed elsewhere, toward Vietnam, toward China, toward the domestic tensions that were reshaping American society in the late 1960s and early 1970s. In 1970, Apollo 13 launched and nearly ended in catastrophe. An oxygen tank exploded on the way to the moon, crippling the spacecraft and forcing the crew, Jim Lovell, Jack Swigert and Fred Hayes, to use the lunar module as a lifeboat for the 4-day journey back to Earth. The mission became one of the most dramatic survival stories in the history of human spaceflight, and it reminded everyone, the public, the politicians, the engineers, how dangerous this undertaking really was. How many things had to go right simultaneously, and how quickly the entire situation could unravel if even one of them did not. Apollo 13 returned safely, but it had reinforced something that was already beginning to feel unavoidable. The moon was not a friendly place to send human beings. Every mission was a gamble, and the more missions flew, the more chances there were for something to go irreversibly wrong. 3 more missions followed, Apollo 14, 15 and 16, each one expanding the scientific scope of the program, each one returning with more lunar samples, more data, more photographs. Apollo 15 brought a small electric vehicle that allowed astronauts to drive across the surface and explore regions they could never have reached on foot. The science was genuinely valuable. Geologists were learning things about the early history of the solar system that could not be learned any other way. But the budget conversations in Washington were moving in only one direction. In 1970, NASA's budget was cut significantly. Several planned Apollo missions were cancelled. What had originally been conceived as a program running through Apollo 20 was truncated. Apollo 17 would be the last. That decision, made quietly in budget meetings rather than in public announcements, is one of the most consequential in the history of human exploration. And it was made not because going to the moon had become impossible, not because the technology had failed, not because the astronauts refused to fly. It was made because the people controlling the money had decided that the return on investment no longer justified the cost. That phrase, return on investment, feels cold when applied to something like lunar exploration. But it is the language that governs large programs in democratic societies, and it is worth sitting with for a moment, because what it reveals is something fundamental about how human civilizations decide what to prioritize and what to abandon. The Apollo program had been funded by fear, not exclusively, not cynically. There was genuine scientific curiosity involved, genuine national pride, genuine admiration for the courage of the astronauts who flew those missions. But the engine driving the money, driving the urgency, driving the willingness to accept risk on a scale that would be unimaginable today, that engine was fear. Fear of Soviet dominance, fear of falling behind in the race for technological supremacy, fear of what it would mean, symbolically and strategically, to let the other side win. Once the Soviet Union effectively conceded the moon race, once it became clear they had not managed to develop a reliable heavy-lift rocket capable of carrying cosmonauts to the lunar surface, that fear began to deflate. Slowly at first, then more rapidly, and without the fear, the money started to look very large relative to the benefits. Apollo 17 launched in December of 1972. It carried Eugene Cernan, Harrison Schmitt, and Ronald Evans. Schmitt was a geologist, the first professional scientist to walk on the moon, rather than a test pilot who had received some scientific training. The mission lasted just over 12 days. Cernan and Schmitt spent more time on the lunar surface than any previous crew, covering more ground, collecting more samples, conducting more experiments. It was in many ways the most scientifically productive of all the Apollo missions. On December 14th, 1972, Eugene Cernan climbed back up the ladder of the lunar module for the last time. Before he did, he spoke a few words that he had clearly prepared in advance, aware that he was closing a chapter of history. He said that he believed humanity's last steps on the moon in the 20th century would not be too long before someone else came back to begin a new era. He believed he was saying goodbye temporarily, that others would follow. He was wrong. Or at least he was wrong about the timeline in a way that none of them could have fully anticipated standing there on the lunar surface in 1972. No human being has set foot on the moon since that moment. The lunar module lifted off, rendezvoused with the command module in orbit, and the three men began the long journey home. Below them, growing smaller with every minute, the moon settled back into its ancient silence. The tracks of the lunar rover still visible, the equipment left behind still sitting exactly where it had been placed, the flag still standing, though the ultraviolet radiation of space would bleach its colours within a few years, leaving it an almost uniform white against the black sky. Back on Earth, the world had changed considerably since 1969. The Vietnam War was grinding toward its end. The Watergate scandal was beginning to unravel the Nixon presidency. The oil crisis of 1973 was approaching, about to deliver a profound economic shock to Western nations. The cultural mood had shifted. The optimism of the early 1960s, the sense that science and technology and national will could accomplish anything, had been tempered by years of social conflict, political disillusionment, and a growing awareness of the costs and limits of unlimited growth. Space exploration did not disappear from the agenda. NASA continued operating. The Skylab space station flew in 1973 and 1974, hosting 3 crews who conducted scientific research in Earth orbit. The Apollo-Soyuz mission in 1975 saw American and Soviet spacecraft dock together in orbit, a symbolic gesture of détente between the two superpowers who had spent the previous 15 years racing to outdo each other. The Space Shuttle program was approved and began its long development, promising a reusable vehicle that would make access to orbit routine and affordable. But the moon receded, not from view. It was still there, rising and setting, moving through its phases, doing exactly what it had always done. But from the active planning of human spaceflight it receded to the background, something that might be returned to someday, in the future, when conditions were right. That someday kept moving forward. There is a particular kind of institutional memory that forms inside large organizations after a major achievement. It is not quite pride, though pride is part of it. It is not quite nostalgia, though nostalgia plays a role. It is something more specific, a way of measuring everything that comes after against the peak, against the moment when everything worked and the impossible became real. NASA, in the decades following Apollo, developed exactly this kind of memory. And in some ways, that memory became both its greatest source of identity and one of its most significant burdens. The engineers who built the Saturn V rocket, still, to this day, the most powerful rocket ever successfully flown, were extraordinary people working at the absolute frontier of what was technically possible. Many of them had come from backgrounds in aviation, in ballistics, in the early missile programs of the 1950s. They had learned their craft in an era when computation was done by hand, when tolerances were checked with physical instruments, when every solution to every problem required a kind of direct, embodied understanding of the machinery involved. They knew their rockets the way a craftsman knows the wood he works with, intimately, personally, through years of accumulated experience with how the material behaves under stress. By the mid-1970s, many of those engineers were retiring. The institutional knowledge they carried, the kind that lives not in manuals or documentation, but in the minds of people who have actually solved specific problems under real conditions, began to disperse. Some of it was captured in reports and technical documents. Much of it was not. Much of it simply walked out the door with the people who held it. This is not a unique problem to NASA. It happens in any field where highly specialized expertise is concentrated in a relatively small group of practitioners. But in the case of human spaceflight to the moon, The consequences were unusually significant, because the Saturn V was not just a rocket. It was the end product of an enormous chain of decisions, compromises, innovations, and hard-won lessons that had taken years to accumulate. Building another one would not simply be a matter of following the blueprints. It would mean reconstructing the entire context in which those blueprints made sense. Some of the manufacturing processes used in the Saturn V no longer existed by the time serious thought was given to returning to the Moon. Certain materials were no longer produced, certain suppliers had closed, certain specialized skills had been passed on to no one. When engineers in later decades studied the Saturn V documentation and tried to understand how some of its components had been manufactured, they occasionally found that the documentation itself was incomplete, that the people who had built the thing had known things they had never written down, because in the moment of building it, those things had seemed too obvious to record. This is one of the less dramatic but genuinely important reasons why returning to the Moon has proven more difficult than it might appear from the outside. It is not that the physics changed. It is not that the Moon moved. It is that the specific human and industrial infrastructure that made Apollo possible was allowed to dissolve, and reconstructing something equivalent from scratch takes time and money that must compete with every other priority a large government manages simultaneously. The Space Shuttle, which first flew in 1981, redirected NASA's focus and resources in ways that would define the agency for the next 3 decades. The shuttle was a genuinely impressive machine, a reusable spacecraft that could carry large payloads to orbit, deploy and retrieve satellites, and eventually help construct the International Space Station. But it was designed for Earth orbit, not for deep space. It could not go to the Moon. It was never intended to. The logic behind the shuttle was sound in its own terms. If you could make access to orbit routine and cost-effective, you could build the infrastructure, the space stations, the fuel depots, the assembly platforms, that would eventually enable missions to the Moon and beyond. Low Earth orbit was supposed to be the first step in a longer staircase. The problem was that the staircase kept getting redesigned before anyone reached the second step. The shuttle turned out to be far more expensive to operate than originally projected. The goal of making spaceflight routine and affordable did not materialize in the way its designers had hoped. Each flight required enormous amounts of maintenance, inspection, and preparation. The thermal protection system, the tiles that protected the orbiter from the heat of re-entry, was particularly labour-intensive. And then, in 1986, the Challenger disaster changed everything. 73 seconds after launch, on a cold January morning in Florida, Challenger broke apart. 7 crew members died. The entire shuttle fleet was grounded for nearly 3 years, while investigators examined what had gone wrong and engineers redesigned the system. When the shuttle returned to flight in 1988, it did so under a weight of additional procedures, additional checks, additional caution that reflected the hard lesson of what happens when organizational pressure leads to the acceptance of known risks. The Moon, during all of this, remained exactly where it had always been. What happened after Challenger is worth understanding not just as a safety story, but as a window into the deeper dynamics of large complex programs and the organizations that run them. Because the investigation into the disaster revealed something that went beyond faulty O-rings and cold weather. It revealed a pattern of decision-making inside NASA that had allowed known problems to be gradually normalized, to be treated as acceptable features of an imperfect system, rather than as warning signs demanding urgent attention. The sociologist Diane Vaughan, who studied the Challenger disaster in depth, called this process the normalization of deviance. It is a phenomenon that appears in many different organizational contexts, not just in spaceflight. It describes what happens when a system consistently produces outcomes that deviate from what was originally intended, and rather than treating those deviations as problems to be solved, the people inside the system gradually begin to treat them as the new normal. The deviation becomes expected, it becomes part of how things work, and eventually the accumulated weight of normalized deviations creates conditions for catastrophic failure. This concept matters for our story tonight because it helps explain something about the gap between what NASA said it could do and what it was actually positioned to do in any given era. The agency had an enormous amount of genuine capability, but it also carried an enormous amount of institutional complexity, layers of management, layers of contractors, layers of competing priorities that made it difficult to move quickly, to change direction, or to take on the kind of bold, focused challenge that the Apollo program had represented. Apollo had worked in part because it had been structured around a single, clear, time-bounded goal. Go to the moon before the end of the decade. Everything else was subordinate to that. Decisions were made quickly because the alternative was falling behind schedule. Risk was accepted at levels that would be considered extraordinary by today's standards, because the political cost of not reaching the moon on time was judged to be greater than the human cost of the missions themselves, a calculation that looks very different in hindsight than it did in the moment. After Apollo, NASA never again had that kind of singular clarity of purpose. Every program that followed was the product of negotiation between the agency and Congress, between different divisions within the agency, between NASA and its contractors, between scientific priorities and engineering capabilities and budget realities. The result was a series of programs that were ambitious in conception and often impressive in execution, but that rarely had the focused momentum of Apollo. Plans to return to the moon were proposed multiple times in the decades following 1972. President George H.W. Bush announced the Space Exploration Initiative in 1989, which included a return to the moon as a waypoint toward an eventual crewed mission to Mars. The plan was ambitious and expensive. Estimates placed the cost at somewhere between $400 billion and $500 billion over several decades. Congress did not fund it. The initiative quietly disappeared. President George W. Bush announced the vision for space exploration in 2004, following the Columbia disaster, in which a second space shuttle was lost during re-entry, killing all 7 crew members aboard. The vision included a plan to retire the space shuttle, develop a new crew vehicle, return humans to the moon by 2020, and eventually send humans to Mars. NASA began developing the Constellation program, a new heavy-lift rocket called Ares, and a new crew capsule called Orion, in pursuit of these goals. And then, in 2010, President Obama cancelled Constellation. Not because the technology was failing, but because an independent review had concluded that the program was underfunded and behind schedule, and that the path it was following would not actually achieve its goals within the timeframes that had been promised. The review recommended a different approach, one that relied more heavily on commercial partners and focused on developing the capabilities needed for deep space exploration, rather than committing immediately to a specific destination. The pattern was becoming visible. Not a conspiracy, not a cover-up. Something more mundane and in some ways more troubling. A cycle of announcement, underfunding, delay, and cancellation that had repeated itself across multiple administrations and multiple decades. Each new president inherited a space program shaped by his predecessor, reshaped it according to his own priorities and political constraints, and left it to his successor in a different condition than he had found it. Meanwhile, the moon waited. Patient in the way that only things without patience can be. Not waiting at all, simply existing, unchanged, indifferent to the plans being made and unmade on the small blue planet 384,000 kilometers below. There is something that rarely gets discussed in the standard telling of this story. something that sits quietly beneath the budget debates and the political decisions and the cancelled programs, something more fundamental than any of those things. It has to do with the nature of the moon itself, with what it actually is and what it actually takes to survive there, even for a short time. When people imagine returning to the moon, they often picture something that resembles the Apollo missions, astronauts in white suits, bouncing across a grey landscape, collecting rocks, planting flags, and that image is accurate as far as it goes. But it does not capture the full reality of what the lunar environment actually does to human beings and to the machines they depend on. Because the moon is not simply an empty, airless desert. It is an environment that is actively hostile to human presence in ways that are subtle, persistent, and extraordinarily difficult to engineer around. Start with the most obvious problem, the vacuum. There is no atmosphere on the moon, none whatsoever. This means that any human being on the lunar surface must be completely enclosed in a pressurized suit at all times. Not partially enclosed, completely. Every breath of air must come from a supply carried from Earth or generated by equipment brought from Earth. The moment any part of that system fails, a seal, a valve, a tube, the consequences are immediate and fatal. There is no margin for error of the kind that exists in environments where the atmosphere itself provides a buffer. The suits used during the Apollo missions were engineering masterpieces, but they were also extraordinarily difficult to work in. They were stiff, physically demanding, and prone to small failures that the astronauts had to manage in real time. The gloves in particular caused problems. Working with gloved hands in a pressurized suit for hours at a time is exhausting in a way that is difficult to appreciate without experiencing it. Several Apollo astronauts returned from their moonwalks with abraded fingernails and damaged hands from the constant physical effort required to manipulate objects through the resistance of pressurized gloves. But the vacuum is only the beginning. The temperature on the lunar surface swings between extremes that dwarf anything experienced on Earth. In direct sunlight, the surface can reach temperatures above 120 degrees Celsius. In shadow, even in the shadow cast by a rock or a piece of equipment, temperatures can plunge to minus 170 degrees Celsius or lower. These swings do not happen gradually, the way temperature changes occur on Earth over the course of hours and seasons. They happen at the boundary between light and shadow, which on the moon is a razor-sharp line. One side of a rock can be hot enough to cook food. The other side, centimeters away, is colder than most places on Earth ever get. This thermal environment creates enormous engineering challenges. Materials expand and contract at different rates. Lubricants that work perfectly in one temperature range freeze solid or become dangerously fluid in another. Electronics that function normally at room temperature can behave unpredictably at extreme cold or extreme heat. The engineers who designed the Apollo equipment had to think carefully about every single component and how it would perform across this entire range of temperatures, often within the same mission. Then there is the dust. Lunar dust is one of the most discussed and least fully appreciated challenges in the entire field of moon exploration. It is not dust in the way we experience dust on Earth. On Earth, dust particles are worn smooth over time by wind, water, and contact with other particles. They are rounded, relatively inert, and easy enough to brush away. Lunar dust has never been through any of those processes. It has been created primarily by billions of years of micrometeorite impacts, tiny particles striking the lunar surface at high velocity and blasting the rock into fragments. Those fragments are sharp. Microscopically, jaggedly, lethally sharp. They are also electrostatically charged, which means they cling to everything, to suits, to visors, to equipment, to any surface they come into contact with. The Apollo astronauts encountered lunar dust immediately and found it to be one of the most persistent and irritating aspects of working on the surface. It stuck to their suits and was impossible to fully remove. It scratched visors, it worked its way into joints and seals. Harrison Schmitt, the geologist who flew on Apollo 17, developed what he described as lunar dust hay fever during his time on the surface, an allergic-type reaction to the dust particles that made their way into the cabin when the astronauts returned from their moonwalks. Other crew members reported similar symptoms. Over a short mission of a few days, these effects are manageable. Over a longer mission, a permanent base, an extended research station, the kind of sustained human presence that would actually be required to make returning to the moon scientifically and economically worthwhile, they become a serious engineering problem that has not yet been fully solved. Alongside the dust and the temperature and the vacuum, there is a threat that is invisible, odorless, and in some ways the most concerning of all: radiation. On Earth, we are protected from the most energetic particles streaming through space by two overlapping systems. The first is the magnetic field generated by Earth's liquid iron core, a vast invisible shield that deflects charged particles and channels them toward the poles, where they produce the auroras rather than bombarding the surface. The second is the atmosphere itself, which absorbs and scatters radiation before it reaches the ground. Together, these two systems reduce the radiation exposure experienced by people on the surface to levels that, while not zero, are low enough to be lived with over an entire lifetime. The Moon has neither of these protections. It has no global magnetic field to speak of, and it has no atmosphere. This means that the lunar surface is exposed directly to the full spectrum of space radiation: galactic cosmic rays streaming in from outside the solar system, solar energetic particles ejected during solar flares and coronal mass ejections, and the constant lower-level bombardment of the solar wind. Every one of these sources delivers radiation to the lunar surface at levels significantly higher than anything experienced by people living on Earth. The Apollo astronauts received radiation doses during their missions that were within limits considered acceptable for the short duration of those flights. But the missions were short, a matter of days, not weeks or months. The cumulative radiation exposure from a longer stay on the Moon, particularly during a period of high solar activity, would be considerably more significant. A major solar particle event, the kind that occurs unpredictably and can deliver an intense burst of radiation over a period of hours, would pose a serious threat to anyone on the lunar surface without substantial shielding. Building adequate radiation shielding on the Moon is possible in principle. The most effective shielding against galactic cosmic rays is mass, large amounts of material between the occupants and space. Lunar regolith, the loose material covering the surface, can serve this purpose if piled thickly enough over a habitat. But the logistics of constructing such a habitat on the Moon, with the tools and materials available, represent an enormous engineering challenge that no one has yet demonstrated the ability to solve in practice. This is worth pausing on because it illustrates something important about the gap between going to the Moon for a few days and actually establishing a sustained human presence there. The Apollo missions were extraordinary, but they operated within a very specific set of constraints that made them possible. The astronauts stayed for short periods. They worked in carefully timed windows. They had the Earth continuously visible and accessible in terms of communication, and they accepted risk levels that were genuinely extraordinary by any modern standard. Several Apollo astronauts later spoke frankly about the degree to which they had been aware of how narrowly some of those missions had avoided catastrophe. Not just Apollo 13, which became famous for its near disaster. Other missions had close calls that were less publicized. Apollo 12 was struck by lightning twice during launch. Apollo 16 experienced a problem with its engine control system that nearly forced the crew to abort the lunar landing. Apollo 17's lunar module was nearly stranded on the surface when an astronaut accidentally broke a critical circuit breaker with his backpack, a problem that was ultimately solved with a felt-tip pen. These were not failures of planning or preparation. They were the inevitable result of operating in an environment so far outside ordinary human experience, with technology that was operating at the very edge of its tested capabilities. The people involved were exceptional. Their training, their composure, their ability to solve unexpected problems under extreme pressure was genuinely remarkable. But the margins were thin in ways that the public, watching on television from living rooms on Earth, could not fully appreciate. The question of how to return to the moon with a level of reliability and safety that modern standards and modern public expectations would find acceptable is therefore not simply a question of political will or funding. It is a genuine engineering challenge. The environment is real, the risks are real, and the gap between a short visit and a sustained presence is far wider than it might appear when you look at the moon rising in the evening sky and think about how close it is compared to the vast distances of interplanetary space. 384,000 kilometers. On the scale of the solar system, barely a step outside the front door. And yet that step has not been taken again in more than 50 years. The reasons are layered, interconnected, and genuinely complex. We have explored some of them: the politics, the budgets, the institutional cycles of ambition and retreat. And we have begun to touch on the physical realities that make the moon a more demanding destination than it sometimes appears. But there is another layer beneath all of this, a layer that involves not just what the moon is, but what we have learned about it since 1972, and how that knowledge has both deepened the scientific case for going back and complicated the question of what exactly we would be going back to do. In the decades following the last Apollo mission, the moon did not disappear from scientific interest. If anything, it became more interesting, not less, as researchers had the time and the distance to properly analyse what the Apollo missions had actually brought back. Because those missions had returned something genuinely extraordinary: 382 kilograms of lunar material collected from 6 different landing sites, representing a sample of the moon's surface unlike anything that could be studied remotely through a telescope or inferred from theoretical models. The analysis of those samples has continued in laboratories around the world for more than 50 years, and what that analysis has revealed has steadily deepened and complicated our understanding of the moon in ways that make it a far more scientifically compelling destination than it appeared to be in 1972. Start with what the samples told us about the moon's origin. Before Apollo, several competing theories existed about how the moon had formed. Some scientists believed it had been captured by Earth's gravity, that it had formed elsewhere in the solar system and been pulled into orbit. Others thought it had formed alongside the Earth from the same cloud of material. Others proposed that it had been spun off from Earth itself during the planet's early molten phase. The Apollo samples effectively resolved this debate, though the resolution took years of careful analysis to emerge. The composition of the lunar rocks, their isotopic ratios, their mineral structure, their age, pointed toward a specific and dramatic origin story that no one had fully anticipated. The moon, the evidence strongly suggested, had formed from the debris ejected when a Mars-sized body collided with the early Earth approximately 4.5 billion years ago. The impactor, which scientists have named Theia, struck at an angle, and the energy of the collision was so enormous that a significant portion of both bodies was vaporized. That vaporized material was ejected into orbit around Earth, where it eventually coalesced, cooled, and solidified into the moon. This hypothesis, known as the giant impact hypothesis, is now the leading scientific explanation for the moon's formation, and the Apollo samples provided much of the foundational evidence for it. The Moon's composition is similar enough to Earth's mantle to suggest a shared origin, but different enough in certain respects to indicate that the impactor contributed material as well. The relative depletion of volatile elements, things like water and carbon compounds that evaporate easily at high temperatures, in the lunar samples was consistent with the extreme heat that would have been generated by such a collision. Understanding how the Moon formed is not merely an academic exercise, it is directly relevant to understanding how the Earth formed, how the conditions for life on our planet came to exist, and how planetary systems in general develop in the early stages of a solar system's history. The Moon is, in a very real sense, a record of the early solar system that has been preserved in remarkable detail precisely because the Moon lacks the geological processes, plate tectonics, volcanism on a large scale, erosion by water and wind, that have erased so much of Earth's early history. On Earth, rocks older than about 4 billion years are extraordinarily rare. The planet's surface has been continuously recycled by plate tectonics, subducted into the mantle and remade into new rock. But on the Moon, rocks from the earliest period of the solar system's history still sit on the surface, essentially unchanged. Some of the samples returned by Apollo have been dated to more than 4 billion years old. They are, in a very literal sense, windows into a time that no longer exists anywhere on Earth. This is one of the most powerful scientific arguments for returning to the Moon, and for going to different parts of the Moon than Apollo visited. All 6 Apollo landing sites were located near the lunar equator, in the near side of the Moon, the side that always faces Earth. This was a deliberate choice driven by practical considerations. The near side was better mapped, communication was direct without the need for relay satellites, and the equatorial regions offered the most favourable conditions for landing and surface operations. But the Moon is a large and geologically diverse world. The far side, the side that never faces Earth, is quite different from the near side in ways that geologists find deeply interesting. The far side has a thicker crust and fewer of the dark volcanic plains, called Maria, that dominate the near side. It may preserve different types of rocks from different periods of lunar history, and its very isolation from Earth means that a radio telescope placed on the far side would be shielded from all the radio frequency interference generated by human civilization, making it potentially one of the most valuable locations in the solar system for certain types of astronomical observation. Then there is the South Pole. The lunar South Pole has become, in recent years, perhaps the most scientifically and strategically important location on the Moon. And the reason comes down to something that would have seemed almost impossible to most scientists working during the Apollo era: water. For decades after Apollo, the Moon was considered essentially dry. The lunar samples contained almost no water. The surface appeared to be one of the most desiccated environments in the solar system. And this made intuitive sense. The Moon has no atmosphere to trap moisture, no liquid water cycle, no obvious source of replenishment. Any water that arrived on the lunar surface through cometry or asteroid impacts, the thinking went, would quickly be broken apart by solar ultraviolet radiation and lost to space. But the South Pole changes this picture entirely. At the lunar poles, the geometry of the Moon's axial tilt creates regions of permanent shadow, craters and depressions that have not seen direct sunlight in billions of years. The temperatures inside these permanently shadowed regions are extraordinarily low, dropping to around minus 250 degrees Celsius in some areas, among the coldest measured temperatures anywhere in the solar system. And in these frozen, lightless places, something remarkable appears to have accumulated over billions of years: water ice. The evidence for lunar water ice has been building since the 1990s through a series of orbital missions that used radar, neutron spectrometers, and other instruments to probe the surface and subsurface of the polar regions. The Lunar Prospector mission in 1998 detected hydrogen concentrations at the poles consistent with the presence of water ice. The L-Cross mission in 2009 deliberately crashed a spent rocket stage into a permanently shadowed crater near the South Pole and analysed the plume of material ejected by the impact, and found water. Not traces, a meaningful quantity, mixed with other volatile compounds in the lunar soil. Subsequent missions have refined and expanded these findings. India's Chandrayaan-1 mission detected water molecules across the lunar surface, including at the poles. NASA's Lunar Reconnaissance Orbiter has mapped the polar regions in extraordinary detail, identifying specific craters and depressions where water ice is most likely concentrated. More recent analyses have suggested that the total amount of water ice at the lunar poles could be substantial, potentially hundreds of millions of tons distributed across both poles. This discovery transformed the strategic calculus of lunar exploration almost overnight. Because water on the moon is not just scientifically interesting, it is potentially the most valuable resource in the solar system relative to the cost of accessing it. Think about what water means in the context of space exploration. It means drinking water for astronauts and crew members, obviously. But more importantly, water can be split into its component elements, hydrogen and oxygen, through a process called electrolysis, which requires only electrical energy, which the moon's surface receives in abundance from the sun. And hydrogen and oxygen are, when combined in the right proportions and ignited, among the most powerful rocket propellants ever used. The same chemistry that produces water can, in reverse, produce fuel. If water ice at the lunar poles can be harvested, processed, and converted into rocket propellant in meaningful quantities, the moon stops being merely a destination and becomes something far more significant, a refueling station. A place where spacecraft travelling from Earth to Mars or elsewhere in the solar system could stop, replenish their propellant supplies, and continue their journeys without having to carry everything they need from the surface of Earth. This is enormously significant because one of the fundamental constraints on all deep space exploration is the tyranny of the rocket equation. To launch mass from Earth into space, you need propellant. But propellant is itself mass, which means you need more propellant to launch the propellant. This feedback loop makes launching anything from Earth's surface into deep space extraordinarily expensive in terms of mass and energy. If you can source propellant from a location with much lower gravity, like the moon, the economics of deep space exploration change dramatically. The discovery of lunar water ice, therefore, did not simply add a new scientific data point. It added an entirely new dimension to the question of why anyone would want to go to the moon. The answer was no longer just about planting flags, conducting science, or demonstrating national prestige. It was about infrastructure, about the possibility of building something at the moon that would make everything beyond the moon more accessible. This realization arrived at roughly the same time as another development that would fundamentally change the landscape of space exploration in ways that no one in the Apollo era could have fully anticipated. It arrived in the form of private companies, not government agencies, not national programs, but commercial enterprises with their own capital, their own timelines, and their own reasons for caring about what might be found and used on the lunar surface. The world of space exploration was about to change in ways that made the old frameworks, the Cold War race, the government programs, the cycles of political ambition and budget retreat, feel like they belong to a different era entirely. And in some ways, they did. For most of the history of human spaceflight, space was a place that governments went. Not because governments were particularly well suited to exploration, history suggests they're not always, But because the costs involved were so enormous, and the timeline so long, and the risks so uncertain, that no private entity had either the capital or the appetite to take them on. Space was, in economic terms, a public good in the most literal sense, something that benefited society broadly, but that the market alone would not produce, because the returns were too diffuse, too distant, and too uncertain to attract private investment at the scale required. This was the assumption that governed space exploration for its first 50 years, and then, gradually, it began to crack. The cracking started not with rockets or moon missions, but with satellites. The communications satellite industry, which had its roots in government programs but rapidly became commercially driven, demonstrated that certain applications of space technology could generate reliable revenue. Companies would pay to launch their satellites, governments would pay for launch services, and if there was a reliable market for launches, there was a reason to invest in making launches cheaper and more dependable. The next crack came from a somewhat unexpected direction. In the 1990s and early 2000s, a generation of entrepreneurs who had made their fortunes in the technology industry began turning their attention to space, not as philanthropists, not as hobbyists, but as business people who saw a genuine market failure, a situation where existing providers were charging far more than the underlying economics of the technology required, and where a new entrant with a different approach could potentially disrupt the entire industry. The most consequential of these entrepreneurs, in terms of what he actually built and demonstrated, was Elon Musk. When Musk founded SpaceX in 2002, the reaction from the established aerospace industry was largely dismissive. Building rockets was hard. Many companies had tried and failed. The technical barriers were real. The regulatory environment was complex, and the incumbents, Lockheed Martin, Boeing, the Russian Space Agency, had decades of experience and established relationships with the government customers who controlled most of the market. What the incumbents underestimated was the degree to which Musk was willing to approach the problem differently. SpaceX did not try to build rockets the way rockets had always been built, with elaborate supply chains, extensive subcontracting, and conservative engineering driven by the assumption that government contracts would cover costs regardless of efficiency. Instead, SpaceX built as much as possible in-house, iterated rapidly, accepted failure as part of the development process rather than treating it as catastrophic, and focused relentlessly on reducing the cost of getting mass to orbit. The Falcon 1, SpaceX's first rocket, failed 3 times before succeeding on its 4th flight in 2008. The company nearly ran out of money before that 4th flight. Musk later said that if it had failed, SpaceX would have been finished. It did not fail, and from that point forward, the trajectory of the company, and of the commercial space industry more broadly, changed decisively. The Falcon 9 became a reliable workhorse of the launch industry, but the development that truly changed the economics of spaceflight was the reusable first-stage booster. For the entire history of rocketry, rockets had been expendable, used once and discarded, their expensive components falling into the ocean after each launch. SpaceX demonstrated, through a series of increasingly impressive landings, that the first stage of a rocket could be recovered, refurbished, and flown again. The cost savings this enabled were significant. The psychological effect on the industry was even more significant. Suddenly, the assumption that spaceflight was inherently and irreducibly expensive began to look less like a law of nature and more like a consequence of how the industry had always chosen to operate. Other companies began investing in reusable rocket technology. Blue Origin, founded by Amazon's Jeff Bezos, developed its own reusable rocket. Rocket Lab developed smaller, more affordable launch vehicles for small satellites. A wave of new entrants arrived, each approaching the problem from a different angle. And as launch costs began to fall, the economics of what was possible in space began to shift. Missions that had previously been unaffordable became achievable. Destinations that had seemed purely aspirational began to appear on actual business plans. The moon was among them. NASA, watching this transformation in the commercial space industry, made a decision that represented a genuine shift in how the agency thought about its own role. Rather than developing all its capabilities in-house, or relying exclusively on the traditional large aerospace contractors who had built the shuttle and the space station, NASA began experimenting with a new model, one in which it acted more as a customer than as a developer. The Commercial Crew program, which ultimately led to SpaceX's Crew Dragon carrying American astronauts to the International Space Station, was an early and successful example of this approach. Rather than NASA designing and building its own crew vehicle, it specified what it needed, offered contracts to companies that could provide it, and allowed those companies to develop solutions using their own methods and their own capital. The result was faster development, lower cost, and a vehicle that has performed reliably across many missions. The same logic was applied ambitiously to the moon. In 2017, NASA announced the Artemis program, its plan to return humans to the moon. The name was chosen deliberately. Artemis is the twin sister of Apollo in Greek mythology, and the program was designed to acknowledge both its heritage and its differences. Where Apollo had been an all-male program driven by Cold War competition, Artemis was explicitly committed to landing the first woman and the first person of color on the moon. Where Apollo had been entirely government-developed, Artemis would rely heavily on commercial partners for key elements of the mission architecture. The centerpiece of Artemis was the Space Launch System, a massive rocket being developed by NASA and its traditional contractors, Boeing and Northrop Grumman, that would provide the heavy lift capability needed to send crew capsules toward the moon. Alongside it, the Orion crew capsule, which had been in development since the Constellation era under a different name, would carry astronauts from Earth to lunar orbit. But the lunar lander, the element that would actually carry astronauts from lunar orbit down to the surface, was awarded through a competitive process to a commercial provider. In 2021, NASA selected SpaceX's Starship as the human landing system for the initial Artemis lunar landing missions. The choice was controversial. Starship was, at the time of selection, still in early development, a massive stainless steel rocket that had flown only to low altitude and had not yet demonstrated the orbital capabilities it would need for a lunar mission. Competitors, including Blue Origin, protested the decision. But SpaceX continued developing Starship at a pace that surprised even skeptics. By 2023 and 2024, the integrated Starship system, the Super Heavy booster combined with the Starship upper stage, had conducted several test flights, each one more successful than the last. The booster demonstrated the ability to return to the launch site and be caught by mechanical arms, a feat that seemed almost theatrical in its ambition but that worked. The upper stage completed flights and demonstrated re-entry capability. The development was not without failures and anomalies, but the trajectory was unmistakably forward. The target date for the first Artemis lunar landing shifted multiple times. Initial projections had suggested 2024, then 2025, then 2026 or later. These delays frustrated observers and gave ammunition to critics who saw in Artemis the same pattern of ambitious announcements, followed by schedule slippage that had characterized previous NASA moon programs. And some of those criticisms had merit. The Space Launch System in particular had proven enormously expensive to develop and costly to operate, with each launch estimated to cost well over $2 billion, which made it difficult to fly frequently enough to maintain meaningful momentum. But something was genuinely different this time. Compared to the programs that had been announced and cancelled in 1989 and 2004, the difference was not NASA itself. It was the ecosystem around NASA. For the first time in the history of lunar exploration, multiple countries and multiple companies were simultaneously pursuing moon-related missions with genuine resources and genuine capability behind them. China had landed robotic spacecraft on the moon. Its Chang'e program had conducted increasingly sophisticated missions, including the first ever landing on the lunar far side, a milestone that required a dedicated relay satellite to maintain communication and that demonstrated a level of technical ambition and execution that commanded serious attention. China had announced plans for crewed lunar missions in the 2030s. Its space program was moving forward with a consistency and a pace that contrasted sharply with the political volatility that had characterized American lunar programs. India's Chandrayaan-3 mission successfully landed near the lunar South Pole in August of 2023, the first spacecraft ever to land in that region, and a milestone that demonstrated India's growing capability as a spacefaring nation. Japan, the United Arab Emirates, and South Korea were all developing lunar programs of their own. The moon was no longer the exclusive territory of two superpowers locked in Cold War competition. It had become a destination for a new and more diverse community of explorers, national and commercial, scientific and strategic, driven by a mixture of motivations that included science, prestige, resource access, and a growing awareness that the rules governing activity on and around the moon had not yet been fully established. That last point, the question of rules, of governance, of who has the right to do what on the lunar surface and what happens when different actors with different interests arrive at the same destination, is one of the most consequential and least publicly discussed aspects of the new era of lunar exploration, and it connects directly to the question of why we have not been back, because the answer is not only about what happened in the past, it is also about what is being negotiated, competed over, and contested right now, in the present. There is a document that most people have never read, and that very few people think about when they look up at the moon on a clear night. It is called the Outer Space Treaty, and it was signed in 1967, 2 years before Apollo 11, at the height of the space race, by the United States, the Soviet Union, and dozens of other nations. It remains to this day the foundational legal framework governing human activity in space. The treaty established several principles that seemed reasonable, even visionary at the time of its signing. Space, it declared, was the province of all mankind. No nation could claim sovereignty over the moon or any other celestial body. Weapons of mass destruction could not be placed in orbit or on the moon. Astronauts of all nations were to be considered envoys of mankind and assisted in emergencies regardless of their nationality. Space exploration was to be conducted for the benefit and in the interest of all countries. These were genuinely noble principles, and for the era in which they were written, an era in which only two nations had meaningful space capabilities and in which the primary concern was preventing the militarization of space and the establishment of lunar military bases, they provided a workable framework. But the Outer Space Treaty was written for a world that no longer exists. It was written before anyone had found water ice at the lunar poles, before private companies had developed the capability to reach space, before the moon had become not just a symbol of national prestige, but a potential site of resource extraction, commercial activity, and strategic competition among a growing number of actors with very different interests and very different legal frameworks governing their behaviour. The treaty's most consequential ambiguity concerns resources. The treaty says that no nation can claim the moon as territory. but it says nothing clear and explicit about what happens when a company, not a nation, but a private entity, extracts resources from the lunar surface. Can a company own the water ice it mines from a permanently shadowed crater? Can it sell that water? Can it establish exclusive rights to a particularly resource-rich location? These questions did not matter in 1967. In the world of the 2020s and beyond, they matter enormously. Different countries have begun answering these questions in different ways, and the answers are not consistent with each other. The United States passed the Commercial Space Launch Competitiveness Act in 2015, which explicitly grants American citizens and companies the right to own and sell resources they extract from space, including from the moon. Luxembourg passed similar legislation in 2017. The United Arab Emirates followed. These laws assert that resource extraction is distinct from territorial sovereignty, that you can own what you mine without claiming the ground beneath it, in the same way that a fishing vessel can own the fish it catches in international waters without claiming sovereignty over the ocean. China and Russia have not accepted this interpretation. Their position, broadly stated, is that the moon's resources are the common heritage of mankind, a principle drawn from a 1979 agreement called the Moon Agreement that was never ratified by any of the major spacefaring nations, including the United States, Russia, or China, and that any framework for resource extraction should be governed by an international body rather than by individual national legislation. NASA attempted to establish a new framework through a set of bilateral agreements called the Artemis Accords, first introduced in 2020. The Accords are not a treaty. They do not require Senate ratification and do not have the force of international law. They are agreements between NASA and the space agencies of partner nations, establishing a set of principles for how signatories intend to conduct lunar activities: transparency, interoperability, deconfliction of activities, preservation of heritage sites, and the right to extract and use space resources. As of the mid-2020s, more than 40 countries had signed the Artemis Accords. China and Russia had not. This division between a group of nations operating under one framework and two major spacefaring powers operating outside it is not simply a diplomatic inconvenience. It reflects a genuine and unresolved tension about who gets to make the rules for humanity's next era exploration and whose interests those rules serve. The south pole of the moon, with its deposits of water ice, has become the focal point of this tension. There are only a limited number of permanently shadowed craters near the South Pole. There are only a limited number of adjacent peaks and ridges that receive near continuous sunlight, and could therefore serve as sites for solar power generation. The most valuable real estate on the moon, in terms of resource access and operational conditions, is geographically concentrated in a relatively small area. If multiple actors arrive at the South Pole with the intention of establishing operations, and if there is no agreed framework for how to allocate access and avoid conflict, the potential for friction is real. Not necessarily military conflict. The Outer Space Treaty prohibits the placement of weapons of mass destruction on the moon and requires that the moon be used exclusively for peaceful purposes. But competition for the same resources in the same locations, without clear rules governing how that competition should be managed, creates conditions that history suggests do not remain peaceful indefinitely. This geopolitical dimension of lunar exploration, the question of who goes, under what rules, with what intentions, has become increasingly difficult to separate from the purely scientific and engineering questions of how to get there and what to do when you arrive. And it adds a layer of complexity to the story of why we have not been back that goes beyond budgets and technology and institutional inertia. Because the moon is no longer simply a destination. It has become, in the language of strategic analysts and space policy researchers, a domain, a place where multiple actors with competing interests will increasingly operate, and where the actions of any one actor will affect the options and security of all the others. This is not so different from how other domains, the oceans, the airspace above nations, the electromagnetic spectrum, have been managed over the course of the 20th century. Each of those domains required the gradual development of rules, institutions, and enforcement mechanisms to prevent competition from becoming destructive. Space is earlier in that process than any of the other domains. The rules are less settled, the institutions are weaker, the enforcement mechanisms are essentially non-existent. And the pace at which actors are arriving at the moon, both national and commercial, is accelerating faster than the governance frameworks are developing. There is a particular concern that space policy researchers have raised with increasing frequency in recent years. It involves the concept of interference, not military conflict in the traditional sense, but the various ways in which one actor's activities on or near the moon could disrupt, degrade, or threaten another's. A lunar base that produces dust through its operations could contaminate solar panels and scientific instruments operated by a nearby but separate installation. A rocket landing near an existing site could damage equipment with its exhaust plume. A communication system operating on certain frequencies could interfere with another operator's signals. A mining operation in a permanently shadowed crater could alter the thermal environment of that crater in ways that affect other users. None of these are hypothetical scenarios drawn from science fiction. They are practical engineering and operational realities that will need to be managed as lunar activity increases. And managing them requires not just technical solutions, but agreements about buffer zones, about operational protocols, about how disputes are resolved when different actors disagree about what constitutes acceptable behaviour. The Artemis Accords address some of these issues, but imperfectly and incompletely. They are a beginning, not a solution. And their effectiveness depends entirely on the good faith of the signatories and on the willingness of non-signatories, most significantly China, to behave in ways that are compatible with the framework even when they are not bound by it. China's lunar program has made it clear, through both its stated goals and its demonstrated capabilities, that it intends to be a major presence on and around the moon in the coming decades. The Chang'e missions have been technically impressive. The plan for a crewed lunar landing, while later in its timeline than NASA's Artemis, is backed by the kind of consistent long-term political commitment that American space programs have rarely sustained. And China has been developing partnerships with other nations, particularly Russia, which signed a memorandum of understanding with China in 2021 to develop an international lunar research station that suggests the emergence of a parallel architecture to the one being built around Artemis. The prospect of two separate parallel systems of lunar infrastructure, one built around American and Allied capabilities and operating under the Artemis Accords framework, the other built around Chinese and Russian capabilities operating under different principles, is not inevitable, but it is a real possibility. And it raises questions that go well beyond the purely technical challenges of getting humans back to the moon. It raises the question of what the moon means, not as a scientific object or an engineering challenge, but as a place where humanity's choices about cooperation and competition, about rules and governance, about whose values and whose interests shape the next chapter of exploration, will be made in concrete and consequential ways. In this sense, the story of why we have not gone back to the moon in 50 years is also, unavoidably, a story about who we are as a species, about the gap between the extraordinary things we're capable of doing when we focus our collective intelligence and resources on a common goal, as the Apollo program demonstrated, and the difficulty of sustaining that focus when the goal is less clear, the competition less defined, and the stakes less immediately legible. The moon is close enough to see with the naked eye, close enough that on a clear night you can make out the dark Maria and the brighter highlands without any optical aid, and yet it has been empty of human presence for more than half a century. Not because we lack the capability to return, but because the reasons for returning, the political, economic, scientific, and strategic reasons, have taken this long to align in a way that makes the journey feel not just possible, but necessary. That alignment is, in the mid-2020s, closer than it has been at any point since 1972. The technology is advancing. The commercial sector is engaged in ways it never was during Apollo. Multiple nations are competing in ways that echo, distantly but recognizably, the dynamics of the original space race. And the discovery of water ice at the South Pole has given the moon a resource value that transforms it from a destination into a potential foundation for everything humanity might want to do beyond Earth. Let's slow down for a moment and sit with something that doesn't get discussed enough when people talk about returning to the moon. Not the politics, not the money, not the engineering, something quieter than all of that. Something that has to do with the human beings who would actually go, who would climb into a spacecraft, leave the only world they have ever known, and spend days travelling toward a place where nothing about the environment is compatible with their continued survival without constant technological mediation. The psychological dimension of deep space exploration is a field that has grown considerably since the Apollo era, and what researchers have learned in the intervening decades complicates the picture of lunar return in ways that are rarely discussed in the same breath as rocket specifications and budget projections. Because sending human beings to the moon is not just an engineering problem, it is a human problem. And the humans involved bring with them everything that makes them human. Their need for connection, their response to isolation, their cognitive performance under stress, their relationship with risk and uncertainty, and the knowledge of what lies outside the thin walls of the vehicle carrying them through space. The Apollo astronauts were selected through a process that filtered for exceptional psychological stability, among many other qualities. They were test pilots, people who had spent careers making calm, rapid decisions in situations where the wrong decision meant death, who had developed through training and experience a particular relationship with risk that allowed them to function effectively in conditions that would be paralyzing for most people. And even they, with all of that preparation and selection, reported psychological experiences during their missions that surprised them. Several Apollo astronauts described a phenomenon that has since been named the overview effect, a profound shift in perspective that occurs when a human being sees the Earth from space for the first time. Looking back at the planet from lunar distance, seeing it as a small, complete, isolated object suspended in absolute darkness, produced in multiple astronauts an emotional and cognitive response that they struggle to put into words. Edgar Mitchell, who walked on the moon during Apollo 14, described an experience of sudden, overwhelming interconnectedness, a sense that the universe was in some way conscious and that his separation from the Earth was somehow illusory, despite the very real 384,000 kilometers of vacuum between them. He spent much of the rest of his life trying to understand and communicate what he had experienced. Other astronauts were more matter-of-fact about the psychological challenges. Michael Collins, who orbited the moon alone in the command module while Armstrong and Aldrin walked on the surface below, later wrote about the experience of being on the far side of the moon, completely cut off from all communication with Earth, more isolated than any human being had ever been, on the other side of a world from his crewmates. He described the experience as one of complete and absolute solitude. Not frightening, he said, but absolute in a way that nothing on Earth quite prepares you for. The isolation of space travel is not simply a matter of physical distance, though the physical distance is real enough. It is also a matter of communication delay, which becomes significant not on moon missions, where the signal travel time is only a little over a second each way, but on any future mission to Mars, where the delay can range from minutes to over 20 minutes depending on the positions of the planets. For a lunar base, the communication delay is manageable, but the isolation is still real, still psychologically significant, still something that must be accounted for in the design of habitats, in the selection and training of crews, and in the support systems that keep people functioning effectively when they are far from everything familiar. What decades of research on isolated and confined environments, Antarctic stations, submarines, simulated space missions conducted in analog facilities, has consistently shown is that human beings in isolation do not simply function at a reduced level of their normal capability. They function differently. Social dynamics shift in ways that are difficult to predict from outside. Small irritations that would be easily absorbed in an ordinary social environment can become sources of significant tension when the people involved cannot simply leave, cannot seek company elsewhere, cannot decompress through normal social activities. Sleep disruption, which is common in unusual environments and unusual schedules, affects cognitive performance and emotional regulation in ways that compound over time. The absence of natural light cycles, natural sounds, natural variation in sensory experience. All of these things affect human psychology in ways that are subtle but cumulative. A mission to the moon lasting weeks or months, the kind of sustained presence that would actually be required to accomplish meaningful, scientific and operational goals, would expose its participants to all of these challenges simultaneously, in an environment where the consequences of impaired judgment or interpersonal conflict could be far more serious than they would be in any terrestrial analogue. The question of human psychological performance under the conditions of lunar habitation connects to a broader challenge that engineers and mission planners have been grappling with for decades: the question of what a sustainable lunar presence actually looks like. Not a short visit of a few days like the Apollo missions, not a flags and footprints exercise, but a real, functioning outpost, the kind of place where people live and work for extended periods, where science is conducted systematically, where the infrastructure of a permanent human presence on another world begins to take shape. This is a qualitatively different challenge from what Apollo demonstrated, and the gap between the two, between a short visit and a sustained presence, is one of the most important and least appreciated aspects of why returning to the moon is more difficult than it might appear. Consider water, which we touched on earlier in a different context. The Apollo missions carried all their water from Earth. For missions lasting a few days, this was entirely practical. A human being requires roughly 2 to 3 litres of water per day for drinking alone, plus additional water for food preparation, hygiene, and other uses. Multiply that by a crew of 3 or 4 over a week, and the total is manageable. Perhaps 100 kilograms or so, depending on how efficiently water is recycled. Heavy, but not prohibitive. Now extend the mission to a month, 6 months, a year. Suddenly the water requirement becomes a different kind of problem. Carrying all of it from Earth becomes logistically and economically unsustainable at anything resembling current launch costs, which is exactly why the water ice at the lunar South Pole matters so much. If it can be extracted and purified, it transforms the sustainability equation of a lunar base in a fundamental way. But extracting water ice from permanently shadowed craters is not a simple operation. The craters where the ice is most concentrated are, by definition, places that never receive sunlight, which means they are among the coldest places in the solar system, and which means that any equipment operating inside them must function reliably at temperatures that push the limits of most conventional engineering materials. The ice itself is not sitting in pure, accessible deposits. It is mixed with regolith, the loose soil of the lunar surface, in concentrations that vary considerably from location to location and that require processing to extract the water from the surrounding material. The technology to do this does not yet exist in a tested, flight-ready form. Multiple companies and research groups are working on it, and there is genuine progress being made. But as of the mid-2020s, no one has successfully demonstrated lunar resource extraction at a meaningful scale. The challenge is not theoretical, it is deeply practical, a matter of building equipment that can operate in one of the most hostile environments in the solar system, survive the thermal extremes of the polar region, extract and process material with minimal human intervention, and do all of this reliably enough to be depended upon as a critical component of a life support system. Power is another fundamental challenge for a lunar base. Solar power, which is highly effective in space, is complicated at the lunar poles by the same geometry that creates the permanently shadowed craters. The sun never rises very high above the horizon at the poles. It circles around the horizon at a very low angle, casting long shadows and making it difficult to capture sunlight with conventional flat solar panels. Certain elevated locations, ridge tops and crater rims, receive near-continuous sunlight and are therefore extremely valuable for power generation. But those locations are limited in number and area, and they are not necessarily close to the resources or the scientifically interesting sites that a base would want to access. Nuclear power is an alternative that NASA and its partners have been actively developing. A small fission reactor, compact enough to be launched from Earth and deployed on the lunar surface, could provide reliable power regardless of the sun's position in the sky. NASA's Fission Surface Power Project has been developing exactly this kind of system, with the goal of demonstrating a working reactor on the Moon in the late 2020s or early 2030s. If successful, it would remove one of the most significant constraints on where a lunar base could be located and how much power it could access. Habitat design is a third major challenge. The habitats used during the Apollo missions were the spacecraft themselves, the command module in orbit, the lunar module on the surface. They were cramped, temporary, and designed for short stays. A lunar base requires something fundamentally different. A space that is large enough to be lived in for extended periods without causing the kind of psychological deterioration that confined environments produce, that provides adequate radiation shielding, that can be pressurized reliably and maintained over months or years, and that can be expanded as the base grows. Several approaches have been proposed and studied. Inflatable habitats, structures that are compact during launch and expand to a larger volume once deployed, offer one possibility. Using lunar regolith as a building material, either pressed into bricks or applied as a thick layer of shielding over a structural frame, offers another. The most ambitious proposals involve tunneling into existing lava tubes, ancient geological structures beneath the lunar surface where molten rock once flowed, leaving behind hollow tunnels that could potentially be sealed and pressurized to create radiation-shielded spaces of considerable volume. Lava tubes on the Moon are thought to be significantly larger than their terrestrial counterparts, potentially hundreds of meters in diameter, because the Moon's lower gravity allows larger underground structures to remain stable. If accessible lava tubes can be found, mapped and engineered into habitable spaces, they could provide a more practical solution to the radiation and thermal challenges of lunar habitation than anything built on the surface. Japan's JAXA space agency has been among the most active in studying this possibility, and the evidence from orbital surveys suggests that suitable lava tube systems may exist in the volcanic regions of the Moon. All of these challenges, the water extraction, the power generation, the habitat design, the radiation protection, are solvable in principle. The physics does not prohibit any of them, but solving them in practice, at the Moon, with hardware that must be launched from Earth, requires a sustained investment of engineering effort, testing, iteration, and refinement that takes years, not months. It requires exactly the kind of long-term commitment that American space policy has struggled to maintain across administrations, and exactly the kind of industrial ecosystem that is now, for the first time, beginning to develop through the combination of NASA investment and commercial sector engagement. There is a version of the future that space agencies and aerospace companies have been sketching out, refining, and debating for the better part of a decade now. It is a vision of the Moon not as a destination to be visited briefly and then left, but as a place where human beings gradually build a permanent foothold, a base that grows over time, that becomes more self-sufficient with each passing year, that eventually serves as both a scientific station and a waypoint for missions reaching deeper into the solar system. It is an ambitious vision, and the closer you look at the details, the more you appreciate both how plausible it has become and how much remains genuinely uncertain. NASA's current plan under the Artemis framework envisions a phased approach. The first crewed lunar landing under Artemis, whenever it ultimately occurs, is conceived not as an endpoint but as a beginning. A demonstration that human beings can return to the lunar surface using a new generation of hardware, a new architecture, and a new set of operational procedures. Subsequent missions would build on that foundation, staying longer, exploring more of the surface, and beginning the process of establishing the infrastructure that a permanent presence would require. The Gateway, a small space station planned for lunar orbit, is a central element of this architecture. Unlike the International Space Station, which orbits Earth at an altitude of roughly 400 kilometers, the Gateway would orbit the Moon, serving as a staging point for missions to the surface and as a place where crew members could live and work between surface excursions. It would be built incrementally, with modules contributed by NASA and international partners including the European Space Agency, the Japan Aerospace Exploration Agency, and the Canadian Space Agency. The Gateway has its critics. Some argue that it is an unnecessary intermediate step, that missions to the lunar surface can be conducted more efficiently and at lower cost without a lunar orbiting station, that the Gateway adds complexity and expense without adding commensurate value. Others argue that it serves important functions, as a communications relay, as a research platform, as a place to aggregate the resources needed for surface missions, and that its value will become clearer as lunar operations mature. This debate reflects a deeper tension that runs through all of space policy. The tension between doing something ambitious now, even if imperfectly, and spending more time and resources building infrastructure that enables more ambitious things later. Apollo resolved this tension decisively in favor of action. It went to the Moon with the hardware available, accepting constraints and risks that a more cautious approach would not have accepted, because the political timeline demanded it. Artemis, operating in a different political environment and without the same forcing function of Cold War competition, has tended toward the more cautious and infrastructure-focused approach. Whether that approach produces better outcomes, or simply produces slower ones, is a question that only time will answer. What is clear is that the architecture being assembled around Artemis is considerably more complex than Apollo's. Apollo used a single rocket, the Saturn V, to launch everything needed for a lunar mission in one shot. The crew capsule, the service module, the lunar module, and all the consumables were stacked together and launched together. Artemis, by contrast, involves multiple vehicles launched separately, and assembled in various configurations before anyone reaches the lunar surface. The Space Launch System launches the Orion capsule. Starship is launched to Earth orbit, refueled there by additional Starship tanker flights, and then departs for the Moon to serve as the lander. The crew transfers from Orion to Starship in lunar orbit, descends to the surface, returns to Starship, and then transfers back to Orion for the journey home. This is a more capable architecture in some respects. It allows for larger payloads and more flexibility than a single rocket approach. But it is also more operationally complex, requires more launches to support each crewed mission, and depends on technologies, in orbit propellant transfer for instance, that have not yet been fully demonstrated at the scale required. Each additional complexity is an additional potential failure point. Each technology that must work correctly for the mission to succeed is another thing that must be tested, validated, and trusted before crew members are placed on top of it. The people designing these systems are aware of all of this. They are not naive about the challenges. They are in many cases extraordinarily talented engineers and mission planners who have spent their careers thinking through exactly these kinds of problems. But awareness of challenges and ability to overcome them on a given timeline are different things, and the timeline for Artemis has slipped repeatedly in ways that suggest the challenges are larger, in practice, than they appeared on the planning documents. There is something worth noticing about the way the conversation around returning to the Moon has shifted over the past decade. The language has changed, the framing has changed, and the change is revealing in ways that tell us something important about where we are as a civilization, relative to the question of what space exploration is actually for. During the Apollo era, the language was almost entirely national and political. It was about America, about freedom versus communism, about demonstrating the superiority of democratic capitalism over Soviet central planning. The Moon was a stage, and the astronauts were actors in a geopolitical drama whose primary audience was not in space, but on Earth, in the living rooms of American voters, in the diplomatic missions of non-aligned nations, in the offices of Soviet officials watching to see whether their rivals could actually deliver on their promises. The science was real, and the scientists involved were genuine in their enthusiasm for what the missions would reveal. But the science was not the reason for the program. It was a justification, a way of giving the program a purpose that would survive beyond the immediate political moment, a residue of value that would remain even after the geopolitical drama had played out. The language today is different. It still includes national prestige. China's growing space capabilities have reintroduced a competitive element that echoes, however faintly, the dynamics of the original space race. It still includes scientific curiosity about the Moon's geology, its water ice, its potential as a record of the early solar system. But it increasingly includes something that would have seemed very strange in 1969, economic language, market language, the language of resource extraction, of commercial opportunity, of return on investment. This shift reflects something genuine about how the world has changed. The rise of the commercial space sector has introduced actors whose motivations are not primarily political or scientific, but economic. These actors are interested in the Moon not as a symbol or a laboratory, but as a place where things of value might be found, extracted and used. Water ice that can be converted to rocket propellant. Rare earth elements that might supplement terrestrial supplies. Helium-3, an isotope that some researchers believe could serve as a fuel for nuclear fusion reactions if fusion technology ever matures to the point of practical use. The economics of all of these resources are speculative, uncertain, dependent on future technological developments that may or may not materialize. But the potential is real enough to attract genuine investment and genuine attention from people who are very careful with their capital. What this means, practically, is that the decision of whether and when to return to the moon is no longer made in a single place, in a president's speech, in a congressional budget vote, in a NASA administrator's strategic plan. It is distributed across a much larger and more complex ecosystem of decision-makers, each with their own interests, their own timelines, and their own definitions of what success looks like. A commercial company deciding to develop a lunar mining technology is making a decision that will affect the trajectory of lunar exploration just as surely as a NASA budget allocation. A bilateral agreement between two national space agencies shapes the landscape of options available to all other actors. A technological breakthrough in propulsion, or in situ resource utilization, changes the economics of the entire endeavor. This distributed, multi-actor, commercially infused landscape is both more resilient and more complicated than the Apollo-era landscape was. More resilient because it does not depend on the political will of any single government sustaining itself across multiple administrations and budget cycles. If NASA's program slips, commercial activity may continue advancing capabilities regardless. More complicated because coordination is harder, rules are less clear, and the potential for competing interests to produce friction or conflict is higher. The Moon, in the mid-2020s, stands at the beginning of what may be a genuine transformation. From a place that humans visited briefly half a century ago and then left, to a place where human presence becomes a permanent feature of the landscape. Not quickly. Not without enormous difficulty and setbacks and moments where the whole enterprise seems to be stalling. But the direction of travel, for the first time since 1972, seems genuinely toward the moon rather than away from it. And yet something about the original question still lingers. Why did it take this long? Why did 50 years pass between the last footprint and the next? The political answers are real, the engineering answers are real, the economic answers are real. But there is one more layer, one more aspect of the story that we have not yet fully explored. It has to do not with what we lacked in the decades after Apollo, but with what we had. With the decisions made about where to direct human ambition and human resources when the moon was no longer the obvious answer, with what the space program became in the absence of a clear destination, and with what that tells us about the way human beings relate to exploration itself, to the impulse to go somewhere new, to push beyond what is known, to stand in a place where no one has stood before. Because that impulse did not disappear after 1972, it went somewhere. And where it went and what it built and what it failed to build is part of the story too. The impulse to explore did not vanish after Apollo. It redirected. And the place it redirected toward, for most of the half-century between 1972 and now, was not the moon. It was not Mars, though Mars appeared repeatedly in plans and proposals and presidential speeches. It was, in a quieter and less dramatic way, the space just above the atmosphere, low Earth orbit, the region stretching from roughly 200 to 2,000 kilometers above the surface, close enough to maintain regular contact with the ground, close enough for resupply missions to be relatively straightforward, close enough that the round trip, in an emergency, could be measured in hours rather than days. Low Earth orbit became the default habitat of human spaceflight after Apollo, the Skylab station of the early 1970s, the Soviet Salyut stations, and then Mir, which hosted cosmonauts continuously for years at a stretch, and taught the world more about long-duration spaceflight than any other program before or since. The Space Shuttle, which made 135 flights over 30 years and carried more people to orbit than all other programs combined. And eventually the International Space Station, the most complex structure ever assembled in space, a collaboration between 15 nations that has maintained a continuous human presence in orbit since November of 2000, without interruption, for a quarter of a century. The International Space Station is an extraordinary achievement. It would be wrong and deeply unfair to the thousands of people who built it, operated it, and lived aboard it, to describe it as anything less. The science conducted there has been genuinely valuable. Research into the effects of microgravity on the human body, on fluid dynamics, on materials science, on biology, that could not have been done in any other environment. The engineering required to build it and keep it functioning is remarkable. The international cooperation it embodies, sustained across decades through political tensions that at various points threaten to tear it apart, is something that future historians may regard as one of the more impressive diplomatic achievements of the era. But the space station, for all its genuine value, did not take humanity anywhere new. It orbited the Earth, over and over and over again, completing approximately 16 orbits per day, never departing from the region of space it had occupied from the beginning. The people aboard it were in space unambiguously, doing things that could only be done in space. But they were not going anywhere. They were circling. There is a particular kind of frustration that accumulated quietly among people who had grown up inspired by Apollo and who had expected that the space station would be a stepping stone toward something further, toward the moon again, toward Mars, toward the outer solar system. The station was supposed to be infrastructure, a place to learn how to live and work in space, so that the knowledge gained could be applied to the harder and more dangerous missions that would follow. In this respect, it was conceived as a means rather than an end. But means have a way of becoming ends when the further goals remain perpetually out of reach. The station became the destination precisely because the destinations beyond it never quite materialized. Each time a new vision for deep space exploration was announced, Bush in 1989, Bush again in 2004, Obama's asteroid mission in 2010, the station remained while the grander plans dissolved. It was the one thing that kept happening year after year, mission after mission, in the absence of anywhere else to go. What this created over time was an interesting psychological dynamic inside NASA and inside the broader community of people who cared about space exploration. The station became both a source of genuine pride and a kind of ceiling, a reminder of how much effort was required just to maintain what already existed, and of how little capacity remained for anything more ambitious. The cost of operating the station consumed a significant fraction of NASA's human spaceflight budget every year. The engineering teams needed to support it were occupied with that support rather than with development of new capabilities. The political will that might have been directed toward a moon program was absorbed by the ongoing work of keeping the station running. This is not a criticism of the people who made those decisions. The station was a commitment, and commitments have to be honored. But it illustrates something important about how large programs in complex institutions work, how they develop their own momentum, their own constituencies, their own logic of continuation that is separate from and sometimes in tension with the broader strategic goals they were designed to serve. The decision to retire the Space Shuttle in 2011 which left the United States without its own crew launch capability for nearly a decade, was in part a reflection of the recognition that the shuttle program had consumed resources that might otherwise have funded the next step. The retirement was intended to free up budget for the development of new vehicles, for the Orion capsule and the space launch system that would form the backbone of Artemis. Whether it actually produced that outcome, or whether the resources were simply absorbed by the development cost of those new vehicles without accelerating their timeline, is a question on which reasonable people disagree. What is not in dispute is that the decade between the shuttle's retirement and the first Artemis launch was a period of genuine constraint for American human spaceflight. NASA astronauts flew to the International Space Station aboard Russian Soyuz spacecraft, paying tens of millions of dollars per seat for the privilege, a situation that produced considerable political discomfort, but that reflected the reality of what had been built and what had not. There is a moment in the history of any long and complicated endeavour where the accumulated weight of everything that has come before, the decisions made and unmade, the programs started and cancelled, the knowledge gained and lost, the ambitions sustained and abandoned, becomes part of the landscape itself, where you cannot understand where you're going without understanding where you have been, not just as history but as context, as constraint, as the specific shape of the possible that the past has carved out for the present. We are at that moment in the story of returning to the moon, everything we have explored tonight, the political origins of Apollo, the fragility of that victory, the dissolution of the infrastructure that made it possible, the cycles of ambition and retreat that followed, the physical challenges of the lunar environment, the discovery of water ice, the rise of the commercial sector, the geopolitical competition taking shape around the South Pole, the unsettled questions of governance and resource rights, the psychological realities of human beings living and working far from Earth, the engineering challenges of sustainable habitation, the shifting language and motivations of the new era of exploration. All of this is present simultaneously in the moment we are in now. It is all active, all relevant, all shaping what happens next. The moon is not simply a destination waiting to be reached again. It is the site of a convergence, of technologies, of interests, of geopolitical dynamics, of scientific discoveries, of commercial opportunities, that is more complex and more consequential than anything that surrounded the Apollo program. Apollo was, in retrospect, a simpler story, a race between two superpowers with a clear finish line, a clear winner, and a relatively short list of actors involved. What is building now is something more diffuse, more distributed, more difficult to narrate as a single story because it genuinely is not a single story. It is many stories happening simultaneously, interacting with each other in ways that are not always predictable, and yet there is a coherence to it if you stand far enough back. The coherence is this. For the first time since the mid-1970s, the moon is being treated by a significant number of serious actors, governments, companies, researchers, engineers, investors, not as a symbol or a memory or a distant aspiration, but as a practical next step, a place to go, a place to work, a place that matters for reasons that are immediate and concrete rather than rhetorical and inspirational. This shift in how the moon is perceived and discussed is itself significant. Perceptions shape investments. Investments shape capabilities. Capabilities shape what is possible. The cycle, once it begins turning in a particular direction, develops its own momentum. Whether that momentum is enough to carry the first crewed Artemis landing to completion, and whether that landing leads to The sustained presence that its architects envision remains genuinely uncertain. Space exploration has a long history of optimism outrunning reality. The graveyard of ambitious plans that never made it off the drawing board is considerably larger than the list of missions that actually flew. But the conditions for success are better now than they have been at any point in the past 50 years. The technology is more mature, the commercial sector is genuinely engaged, the scientific motivation is clearer and more concrete. The geopolitical pressure, while different in character from the Cold War competition that drove Apollo, is real and growing. And the accumulated knowledge of what does and does not work, from the engineering lessons of Apollo, from the long-duration spaceflight research conducted on Mir and the International Space Station, from the robotic missions that have mapped the Moon in extraordinary detail, is available in a way that it was not during the original race. The footprints are still there. In the fine grey soil of the Sea of Tranquility, and in 5 other locations scattered across the near side of the Moon, the evidence of what was accomplished half a century ago sits perfectly preserved in the airless silence. No wind has touched them. No rain has softened their edges. They are as sharp and clear as the day they were made, waiting with the patient indifference of geology for whatever comes next. What comes next is being decided now. In engineering laboratories and government budgets and corporate boardrooms and international negotiations and university research programs, and the imaginations of people who look up at the Moon on a clear night and feel something that is not quite nostalgia and not quite ambition, but somewhere between the two, a sense that what was done once can be done again, and that what was done again can eventually become something that was never done before. The Moon is not going anywhere. It rises and sets on its ancient schedule, indifferent to our plans and our politics and our hopes. It has been doing this for 4.5 billion years, and it will continue doing it long after whatever we build on its surface has crumbled back into dust. But in the window of time we inhabit, in these particular decades at the beginning of the 21st century, the question of what humanity does with the Moon, and why, and how, and under whose rules, is one of the more consequential questions being asked anywhere on Earth. There is a generation of people alive today who have never known a world in which a human being has walked on the Moon. For them, and they now constitute the majority of the world's population, the Moon landing is not a memory. It is a story. This matters more than it might seem. When the people making decisions about space programs have a living personal connection to what was accomplished before, when they remember watching the Apollo launches, remember where they were when Armstrong spoke from the surface, they carry a particular kind of motivation that is difficult to replicate through documentation alone. That living connection is now largely gone. The engineers who built Saturn V are gone. The astronauts who flew to the Moon are in their 80s and 90s. The direct human thread connecting the present to the last time anyone stood on another world is approaching the point at which it will be entirely historical rather than partly living. And yet something interesting has happened in the absence of that memory. A new generation has developed its own relationship with space, one less constrained by the Cold War context. Young engineers who grew up watching SpaceX boosters land on drone ships, who followed Starship through webcasts, who were captivated by James Webb images, bring a different kind of enthusiasm, not diminished, different. This shift is visible inside NASA itself. The culture today is more cautious, shaped by Challenger and Columbia, by hard experience with how catastrophically wrong things go when safety culture erodes, more diverse, more interconnected with commercial partners than the relatively self-contained Apollo-era NASA ever was. Whether this culture is better suited to building a sustainable lunar presence is a question without a clean answer. The caution is valuable, the diversity is valuable, the commercial connections are valuable. But there are moments, in long approval processes, in extensive review cycles, when you can sense the ghost of a different urgency, the kind that does not ask how many reviews a decision needs, but simply asks what needs to happen and who is going to make it happen by when. Apollo was a triumph of exactly that urgency. Its methods would not pass modern safety reviews. Its speed of development would be impossible within today's frameworks. But it worked. It got people to the moon within a decade of the decision being made. The question now is whether the new approach, slower, more careful, more distributed, can produce something more durable. Apollo was a sprint. What is being built now is intended to be a marathon, and marathons require a very different relationship with the long middle sections, where the finish line is not yet visible but the starting line is far behind. As the night deepens, it is worth pausing to notice something about the moon itself, something that has nothing to do with politics or engineering or commercial opportunity. But that might be the oldest and most persistent reason human beings have ever had for caring about that pale disk moving through the sky. The moon has been there in essentially its current form for as long as human beings have existed. Every civilization has looked up at it, named it, woven it into stories, built calendars around its phases. Early humans tracked its cycles on bones and stones. The Lascaux cave paintings may include a lunar calendar. Stonehenge incorporates lunar alignments. The earliest written calendars from ancient Mesopotamia were lunar. The moon governed agriculture, navigation, religion, and ritual across virtually every culture that has ever existed. All of this is still present, embedded in language, in the structure of our calendars, in the words for months and lunacy, in the reflex that makes people look up when the moon is full. When the Apollo astronauts stood on the lunar surface and looked back at Earth, they were experiencing something that had never happened before in human history. The vantage point had been reversed. For all of human existence, the moon had been the thing in the sky people looked at from the Earth. For the first time, human beings were on the moon, looking back. Harrison Schmitt, on the last day of the last Apollo mission, described feeling not separation but connection, the Earth seeming more present, more vivid, more intimately known than it ever had from its surface. This paradox keeps appearing in the accounts of people who have travelled in space, that leaving the Earth clarifies your understanding of it in a way that staying on it never quite does. You cannot see the shape of something from inside it. What would it mean for thousands, eventually tens of thousands, of people to have that experience? It is not the kind of argument that shows up in mission architecture documents, but it may be, in the very long run, the most persistent reason the impulse to go keeps reasserting itself across generations and budget cycles. The moon is the closest place we can go to have that experience, the first step, modest in cosmic terms, but enormous in human ones. And the perspective, once gained, is not easily forgotten. There is a question that surfaces whenever the conversation about returning to the moon becomes specific enough to involve actual timelines and actual hardware and actual human beings sitting on top of actual rockets. The question is not technical. It is not political. It is something older and more personal. Is it worth it? Not in the abstract. Worth it for the specific people involved. Worth it for the families who wait on the ground. Worth it for the engineers who carry the weight of knowing that if they miss something, someone dies because of it. Worth it for the societies that must decide, election after election, whether the money and the risk are justified by the returns. This question has never had a clean answer. The people who have gone into space have generally answered it for themselves before they went. But that private accounting happens in the context of a public one that is always being renegotiated. The history of exploration is full of these renegotiations. European societies funded voyages that cost enormous amounts of money and killed enormous numbers of people, and then, at other times, pulled back and decided the costs were too high. Space exploration sits within this longer history. The specific technology is new, but the underlying tension between the urge to go somewhere new and the calculation of what going there costs is ancient. What has changed is the nature of the calculation. During Apollo, it was primarily political, measured in Cold War prestige and deterrence. Today it is more complex and more distributed. The scientific returns are clearer. The economic returns are more tangible, if still speculative. The geopolitical stakes are real, and there is a category of return that is harder to quantify: the human return, the transformation that happens in people who go and in the cultures that send them. What is striking about the current moment is that this weighing is happening simultaneously in many different places, among many different kinds of actors, without any single authority making the final call. Governments, companies, scientists, engineers, and the public are all making their own calculations, continuously and usually without much explicit awareness that they are doing so. The result is not a clean answer. It is a messy, ongoing negotiation, which is exactly what you would expect from a civilization trying to decide what to do next. And within that negotiation, slowly, and with many setbacks still to come, the balance appears to be tipping toward going. Not because anyone has solved all the problems, but because enough different threads, scientific, commercial, geopolitical, human, are pulling in the same direction at the same time for the first time since the 1970s. The moon has waited this long. It can wait a little longer, and the waiting, when it ends, will matter in ways that will take decades to fully understand. Ecco la versione accorciata. The story we've been moving through tonight is, in the end, a story about time, about the relationship between what human beings are capable of in extraordinary moments and what they are capable of sustaining across the longer, less dramatic stretches that connect those moments. Apollo was a moment. It compressed an extraordinary amount of human capability into a decade and produced results that still seem, half a century later, almost improbable. 12 human beings walked on another world, and then they came home, and the moment passed, and the sustained effort that would have been required to build on what was accomplished did not materialize. This is not a failure unique to space exploration. Great crises produce great responses, mobilizations of collective will that are impossible to sustain indefinitely, but that, in the acute phase, produce remarkable things. And then the crisis passes, the momentum dissipates, and years later people wonder how so much was achieved so quickly and then seemingly abandoned. Apollo was not abandoned because the people involved stopped caring. Gene Cernan, the last man to walk on the moon, spent much of the rest of his life arguing for a return, convinced that what had been accomplished was a beginning that had somehow been mistaken for an ending. He was right that it was a beginning. What he could not have anticipated was how much would change during the pause. The Soviet Union dissolved. Room-sized computers shrank to pocket devices. The commercial space, industry emerged from nothing. China became a spacefaring nation. Water ice was found at the lunar poles. The James Webb Space Telescope returned images of the early universe no one had ever seen. All of this happened while the moon waited, while the footprints remained undisturbed, while the flags bleached white in the ultraviolet light of an unfiltered sun. The pause now appears to be ending, not dramatically. There is no single moment analogous to Kennedy's speech, no clear before and after. But the direction of travel has changed. The resources being committed are real. The capabilities are real. The competition is real. The water is real. The next human beings to stand on the moon will carry with them everything that happened in the 50-plus years since Cernan climbed that ladder. The knowledge from decades of robotic exploration, the engineering lessons of the space station and the commercial sector, the weight of the question, why did it take so long, and a lived understanding of all the complicated true answers beneath it. They will also carry something the Apollo astronauts did not. The awareness that what they are doing is not a beginning but a continuation, a return to a thread that was dropped and is now being picked up again. The moon is not a destination to be reached and then left. It is a place with resources, history, scientific value and strategic significance that human beings are committing to in a more permanent way. And there is still, despite everything we know, a great deal of moon left to discover. The far side remains largely unexplored. The subsurface is almost entirely unknown. The lava tubes have never been entered. The universe has a long history of being stranger and richer than the models predicted. There is still, in other words, a great deal of moon left to discover. Let the night settle around you for a moment. Whatever time it is where you are, take a breath and let the weight of everything we have moved through tonight rest, without needing to be resolved. Because this is, ultimately, a story without an ending, not yet. The next chapter is still being written, in engineering laboratories and government meetings and the minds of people who have spent their careers preparing for something that has not yet been attempted. The story is live. The outcome is genuinely uncertain. What we explored tonight was a question that seemed simple. Why haven't we been back to the moon? And that opened onto something much larger. Cold War politics, budget mathematics, rocket physics, lunar dust chemistry, the psychology of isolated human beings, the economics of a commercial sector that didn't exist when the last footprints were made, and the deep human impulse to go somewhere new and look back at where you came from. None of these things, alone, explains the 50-year pause. All of them together come closer, but even together, they leave something unaccounted for, some remainder that resists explanation. Perhaps the pause was simply what was needed. The reusable rockets, the commercial ecosystem, the understanding of the lunar environment, perhaps none of it could have existed in 1972. Perhaps going back before all of that was in place would have produced another Apollo, another extraordinary moment that could not be sustained. Perhaps the pause was not a failure, but a preparation. The world of the mid-2020s is genuinely better positioned for a sustainable lunar presence. The technology is more mature, the ecosystem is more diverse and resilient. If the next return leads to something that lasts, a presence that is maintained, a beginning that is not mistaken for an ending, then the waiting will have been part of the story. Tonight, somewhere above you, the moon is doing what it has always done, moving through its ancient orbit, reflecting sunlight onto the darkened side of the Earth, rising and setting over billions of people who are sleeping or waking, most of them not thinking about the moon. But some of them are. Somewhere, an engineer is running a simulation that ends at the lunar South Pole. Somewhere, a young person is watching a launch webcast and feeling the particular excitement of watching something leave the Earth. Somewhere, 2 astronauts are training in a simulated lunar habitat, practicing the routines of a life that does not yet exist but is being prepared for as if it does. All of that has brought us to now, to a point where the question of whether we go back is no longer really a question. The question now is what the going becomes, what it builds, what it lasts into. You are part of that too, not as a spectator. The moon belongs to everyone who has ever looked up at it, and understanding the real story, with its full complexity, is part of how that choice gets made well rather than badly. So if you remember nothing else, the footprints are still there. The water is real. The moon is close enough to touch, almost literally, in the scale of the universe. And somewhere in the not-too-distant future, human beings will again stand on the surface of the moon and look back at the Earth. Not to complete a return journey, but to begin something that, this time, will not need to be repeated from scratch 50 years later. The moon is waiting. And for the first time in a long time, we are genuinely on our way. Sleep well tonight. You're lying beneath the same sky that the Apollo astronauts launched through. The same sky that the next crew will one day rise through. If this journey stayed with you tonight, leave a comment and tell us where you're listening from. Drop a like if you found something worth keeping. Subscribe if you want to keep making these long, unhurried journeys. And to every person who has ever looked up at that pale disk and felt something, you were right to feel it. Good night.